Hello, we are done with calculus and we're going to continue with vectors. In this chapter I'm going to cover geometric vectors, while in the next chapter I'm going to talk about algebraic vectors or Cartesian vectors. And we're going to finalize the course with one more chapter in which we basically apply these vectors for reasons that you're going to see at that time. Now, you may wonder, why do we have two types of vectors, geometric and Cartesian? They are basically the same vectors. What's different is the way we describe them. So I'm only gonna focus on geometric vectors, especially here, because I'm going to explain the Cartesian ones later, like I said. But first of all, what is the definition of a vector? Let's define one officially. We already talked about vectors in the second chapter when we talked about displacement, velocity and acceleration. So a vector is a quantity that has size or magnitude and direction. As soon as it has a direction besides magnitude, it's a vector. A scalar is a quantity with size only. Now, to make everything more clear, I'm going to show you some examples of scalars and vectors, and eventually some connection between some of these quantities. For scalars, the most common are numbers. Numbers that we used all the time in the past, and we're going to continue to use, like 1, 2.3, minus 4, square root of 5, any number basically. So integers, rational numbers, all real numbers basically, regardless if they are negative or positive, they are just scalars. They don't have a direction, they just have a value. Another example would be temperature. This is something that you are going to encounter in so many problems. I can read the temperature to be negative 11 Celsius degrees, or maybe 128 Fahrenheit degrees, but there is no direction for this. So it's only magnitude, it's a scalar. Another common scalar that we're going to encounter is the area. You may see values such as 1 square meter or 300 square centimeters. This is just a magnitude. The distance only gives you the length, right, between 2 points. So it's 1 meter, 100 kilometers. It's just a size for the distance. There is no direction. The speed, we express it as 1 meter per second or 100 kilometers per hour, but there is no direction attached to it, so it's only a scalar. Mass, it's also a quantity that we're going to work with quite a bit. So 1 gram, 60 kilograms, makes no difference. It's only a magnitude. There is no direction attached to this. Now, let's look at some examples of vectors. Displacement, for example, which is the correspondent of distance. But if I say 1 meter at an angle of 75 degrees, that's already a vector. It's a displacement vector because it has a direction attached to it, not just the dimension of the distance. Velocity is the correspondent of speed in the world of vectors, because we're going to express these such as 60 kilometers per hour south. So I already know not just how fast, but I know in what direction am I heading. Force, 10 newtons upwards, it's already clear we are dealing with a vector. Hopefully it's a lot more clear now what vectors are. Let's see how we can denote these vectors. One method to describe a vector would be in words. For example, if I say 1 meter at 45 degrees from the horizontal, I just described in words a vector. This is how you're going to encounter it in many problems. And when you encounter something like that, you should understand what that represents. We can represent these vectors in a diagram. So the vector I just described earlier in words, I can represent it such as this. As you see, I have a vector that is 1 meter long and it's 45 degrees from the horizontal, like I just said. And this is a graphical representation, a diagram. And of course we want to express this in symbols. We can use the following symbols: AB with this arrow on top of it, or simply U, a small letter U, or any other letter for that matter. As usual, we use capital letters for describing vertices and small letters for describing sides or lengths. A vector such as this AB, A represents the start point or the tail of the vector, while B is the end point or the head of the vector or the tip. I like you to pay attention to the order of these letters. So AB as a vector is not the same with BA. One more thing you're going to encounter when working with vectors is the magnitude of a vector. So for this vector AB, I'm going to write it this way. You put these vertical bars, which look very similar to what you already know as absolute value, and it's not just a coincidence, that's actually what it means. Okay, so I'll leave it at that, but for now I just want to go a little further with some of this terminology and notations. I already told you in the beginning that we're going to talk about geometric vectors throughout this chapter. What makes these geometric vectors different than Cartesian vectors is that they are not related to a coordinate system. However, it's essential for a vector to have a direction. So in order to be able to describe this direction somehow, geometric vectors, as you've seen in the examples I gave you a moment ago, we either refer to references from the world surrounding us, like an angle from the horizontal, some particular angle from the vertical, up, down, left, right. But in navigation, for example, we have cardinal points. Therefore, let me introduce a couple of ways in which we can use these cardinal points in order to describe the direction of a vector. So we're going to talk about true bearing, also known as azimuth bearing, or simply bearing. If you hear only bearing, it's referring to true bearing. This is represented by the number of degrees that you can measure from the north direction to the direction of your vector, measured in a clockwise direction. As you can see on this example, if I have a vector pointing in the first quadrant, I can read 45 degrees. That would be a bearing of 45 degrees. Alternatively, there is the so-called quadrant bearing. This is a similar notation, however, the number of degrees in your notations are only going to be between 0 and 90 degrees. And there is a rule here that we should follow. We take north or south direction as a reference, and we measure how many degrees towards east or west from these directions, keeping in mind that this quadrant bearing should only take values between 0 and 90, because it's a quadrant, right? 90 degrees only. So for example, if I have a vector such as this, 60 degrees, if I measure from north direction, I can express this as a quadrant bearing such as, and I'm reading it this way, I'm writing it as you see, but I'm reading it as follows: 60 degrees west of north. So the reference is always coming first and followed by the number of degrees in which direction are those degrees measured. Or let me take another example to make it more clear eventually. For example, if I have this other vector that I sketched in blue, I can measure 30 degrees from south towards east. How am I going to write this? It's going to be S30E, but I'm reading this as 30 degrees east of south. And it makes sense to read it this way and to write it as it is. Now, it's commonly to use north and south as reference, but people use east and west as reference as well. Anyway, I'm going to use only north and south directions for reference throughout the course, and I would appreciate it if you do the same. Now that you know quite a bit about vectors, let's have a look at a few relationships that we're going to encounter between two or more vectors that we need to identify and to understand very clearly from the beginning. When we talk about parallel vectors, what that means is, like in the example you see here, I have two vectors u and v. They have the same direction, even though their magnitude is different, as you can notice. By the way, the length of this line, the vector itself, is important. It's usually drawn to scale, so if you see two lines that are not equal in size, then that should be very clear for you that the magnitude of these two vectors is different. Parallel vectors only have to have the same direction regardless of the magnitude. So I can write u parallel to v. However, I can have a vector such as w here, which is short, but you see, it's parallel to the other lines, even though has an opposite direction. Well, this is also parallel. So parallel vectors are those that are having the same direction or opposite direction, and the magnitude of these vectors doesn't matter. Equivalent vectors. For equivalent vectors, let's look on this diagram. PQRS. As you can see, I put some arrows there. It's a parallelogram, right? So we know that opposite sides are parallel and equal in size. Therefore, we can say that the vector SP is equal, or it's equivalent to RQ. Notice the order in which I took the letters. I said SP equals to RQ. S being the start point, P being the end point, then it has to be the same with RQ since it points in the same direction. Another example on this diagram would be PQ, which is equivalent to SR, for example. There are plenty more other sets of vectors that are equivalent on this parallelogram, but I'm just going to resume at that. Those are equivalent vectors with the same magnitude and the same direction. Now, we're also going to encounter opposite vectors. And on the same diagram, first I'm going to just express the opposite of one vector, PQ. I can denote that with minus PQ or negative PQ. Or I can just write this in a reverse order of the letters. So that's why I told you it's very important to put the letters in the right order, because PQ and QP are opposite vectors. Of course, you can choose groups of other two vectors, such as PS and RQ are opposite vectors as well. So I hope it's all clear, and if so, I'm going to conclude this lesson here. Thanks for watching.